In this section, we're going to look at quadratic functions, and we're going to talk about some of the properties of quadratics, and then look at some of the graphing properties of quadratics. Okay. A quadratic function is any function of the form f of x equaling ax squared plus bx plus c, where a does not equal 0. This is what we call a quadratic function, mostly because the degree on the variable, the highest power of the degree is 2, which means it's going to give us more than one solution. The standard form for a quadratic is f of x equals a times the quantity x minus h squared plus k. This form can usually be found by completing the square. So we can do an example or two of that if you don't remember how to complete the square on a quadratic. And the standard form is nice because it gives us a lot of information about the graph of the function as well as the function itself. The first thing to note is that the domain for this is all real numbers. So it doesn't matter what I plug in for x, I can always get a real number out. This form also tells me what the vertex of the quadratic is. So if I am looking at my quadratic function, wherever it may be, there would be the vertex of my quadratic. And in this particular instance, I'm just looking at one where my a value is greater than 0, so it's opening upward, which tells me that my range is going to be from k to infinity, meaning from this point up to infinity. If my a happens to be less than 0, then I get the other side of this. I'll get my quadratic that's opening downward. Again, there's my vertex at hk. And then in this instance, my range is going to be from negative infinity up to the value k. Okay. So again, if I can get it in the standard form, it gives me a lot of information about the graph of this. Okay. The other information we can pull from a quadratic is that if I know it's in this standard form, I can also determine where the local minimum and the local maximum are. So if you remember from earlier sections or earlier courses, the local extrema, meaning the maximums and minimums, are where my function has a high or a low point within a small interval. So for a minimum, it means that in some interval, it is the smallest point on the graph. And so in this case, again, if I'm looking at my parabola that's opening upward, then we can say that this is the local minimum. And again, that just happens to be the vertex. Okay? If a is less than 0, then I get just the opposite. It's going to be opening downward, and this becomes our local max. Now, one of the things to make note of here is if I am looking at an upwards parabola or a parabola where my a is greater than 0, there is no maximum for this because, as we saw before, our range goes to infinity. And so, in this case, there's no highest point, so there's only a local min. And likewise with a parabola opening downward. So if a is less than 0, in this case, I'll have a local max, but there is no minimum value. In this case, it's going to go down to negative infinity. Okay. Now, again, this standard form is nice so that we can actually pull off some of this information. But in some cases, maybe we are just looking for the vertex, and it's not necessarily worthwhile to go through completing the square to come up with the equation. So if we're given the quadratic in its quadratic form, I can find the vertex in another manner, and that is I'm going to look at ax squared plus bx plus c. I'm going to pull off a and b, and then I can find the ordered pair for the vertex by looking at x equaling negative b over 2a, and the y being f of negative b over 2a. Okay? This will give me the vertex. Again, I can look at whether a is positive or negative, and again, that will tell me whether I'm looking at a max or a min. So in this case, if we're looking at our picture, let's say I'm looking at something like this, then this point here would be at negative b over 2a. This point is going to be f of negative b over 2a. And so there would be my maximum. Okay. Likewise, we can do the same thing with the min. So given a parabola opening upward, if there's my low point, again, there would be my negative b over 2a. So that's the x-coordinate. This would be my f of negative b over 2a. There's my y-coordinate. And again, this point being our vertex would be a minimum value. So let's look at an example of finding the vertex given our quadratic equation. So in this case we have a quadratic function, 2x squared minus 5x plus 2, that we want to find the vertex two different ways and then be able to determine whether it's a maximum or a minimum. Okay? So again, the two ways we can do this is to complete the square or to use our negative b over 2a. Okay? So I'm going to start with completing the square because again, that's probably the one that most people don't remember how to do easily. Okay. So given my function, to complete the square again, the first thing I need to do is factor the coefficient out of my x terms. So I'm going to pull a 2 out of both of my x terms. And then we want to rewrite these x terms so they are a perfect trinomial. And a perfect trinomial just means one that I can factor into a binomial squared. So to do that, I'm going to take half of this middle term, so half of 5 halves is 5 fourths, and I'm going to square that. Okay. Again, because it's equality here, whatever I do here, I need to make sure that I equal it out. So this plus 2 stays, but then I'm going to have to do the opposite of 2 times 25/16. Which we can multiply out to get 25 over 8. We'll make it negative so that it cancels out and I have not changed the problem. From there we can rewrite. So now we've got our perfect trinomial, which we can rewrite as a binomial squared. And again, one of the easy ways to determine this, if you can't factor this nicely, I think it's square root of the first term, square root of the last term, and the first sign between them. Okay. Over here we'll get a common denominator, so we can think 16/8 minus 25/8 looks like a negative 9/8. Okay. And so there is our function in its standard form. So this tells us our vertex is going to be 5 over 4, negative 9 over 8. And here again, be careful of your signs. Remember, it's x minus h. So in this case, h is positive 5 fourths. And k is, well, it's plus k, so k is whatever is on the outside there. So there's our vertex using the completing the square method. Now, again, we want to do this two different ways. So one way we can check to make sure that we got the right vertex is to use the other method, which just goes back to our regular formula there. It says if I look at negative b over 2a, negative b is negative of negative 5, and 2a is 2 times 2. And so we can see here we're going to get 5 over 4, which matches. And then f of negative b over 2a says we're just going to plug 5 fourths into our function. So 2 times 5 fourths squared minus 5 times 5 over 4 plus 2. Okay, and we can simplify, so we'll get 25 over 16 times 2, which is 25 over 8, minus a 25 over 4 plus 2. If we get a common denominator through here, which is going to be 8, we can see we'll get 25 minus 50 plus 16 all over 8. This looks like 41 minus 50, which looks like a negative 9 over 8. Okay. So here again we see that our vertex is 5 over 4, negative 9 over 8. Okay, so there's two different ways to get your vertex for that particular problem. And again, both ways are useful because it's a great way to check and make sure that you got the right thing. So if I'm not sure I completed the square correctly, I can do the negative b over 2a and see that I get the right answer as well. Okay, and then the second part of this is we want to determine whether this is a min or a max. And here, again, the only thing we need to do is look at our a value. Okay, and it doesn't matter if we're looking at a in the quadratic form or a in the standard form. Notice they're exactly the same. And then, so in this case, if we look, a is greater than 0, which tells me my parabola is opening upward, so this is a min. Okay, so there is our solution to that problem. So next, let's look at a couple of word problems or applications. Most of your functions that you're going to be looking at within this course are going to ask you to model different situations. And so some of those modeling problems, you are going to be given the functions or the equations and asked to use them to determine information about the situation. In other cases, you're going to be asked to come up with the function and then use that to find information about the situation. Okay, so here's a couple of examples. In this first one, we've got a ball that is thrown upward with a velocity of 40 feet per second. Its height in feet after t seconds is given by y equal 40t minus 16t squared. We want to find the maximum height that the ball will reach. Okay, so in this case, we're already basically given our function. We're told that y is equal to 40t minus 16t squared. Okay, so there's our quadratic. It's not in its standard form, it's not in its quadratic form, but again, we've got a square on our variables, so we know it's a quadratic. Okay, so to determine the maximum height, well, remember, the maximum is going to occur where the vertex is. So in this case, I just want to find the vertex of this. And again, in this case, since I don't really care about graphing this or finding other information, I just need the vertex, I'm going to use the negative b over 2a formula. So negative b over 2a says that in this case, a is negative 16, and b is 40. So we'll simplify this. Looks like a negative 40 over a negative 32. We can pull an 8 out of top and bottom. So it's going to look like 5 over 4. Okay. Now, this, again, if we think about this, this is our domain variable. This is t. So when t is 5/4, that's the x-coordinate or the t-coordinate of my vertex. And so then when t is 5/4, that just tells me when it's going to reach there. So this is in seconds. I still need the height. So here, I'm going to need to find f of 5 over 4. Okay, in other words, I'm going to plug this into y and determine what the value is going to be. So 40 times 5 over 4 minus 16 times 5 over 4 squared. We want to simplify that down, and that's going to give us our maximum height. So simplifying here, it looks like 50. Here, when we rewrite, we'll go ahead and square that. We can see the 16s cancel out. So there's the y-coordinate for our function. This again is measured in feet. So this tells me that 25 feet is going to be the max height. Okay. And again, there are other ways you can check this. You can use the completing the square, and you can find the vertex, and you should find that it's 5/4 25. But this way, again, because we don't need any other information, that's a nice way to go. In this next example, a manufacturer finds that the revenue generated by selling X units of a commodity is given by R of X equaling 80X minus 0.4X squared, where R is measured in dollars. We want to find the maximum revenue and the number of units that are required to be made to obtain this maximum revenue. Okay, so this is another example of one where you're given the function and we just need to basically use the function to get information. So here again, if I'm looking, R of X is equal to 80X minus 0.4X squared. This is very similar to the last example where I am trying to find the vertex. So again, the maximum there means I'm looking for the high point. And again, because it's this quadratic, I know I'm looking at a parabola. Okay. Now, this one, even though it's very similar to the last one, I'm actually going to use completing the square on this. And again, it's because for both of these problems, you can use either method to solve. So the last one we did the negative b over 2a, so this one we'll go ahead and complete the square. So in this case, if I look, R of X, I'm just going to rewrite this so it looks like it's in the right form. And I'm going to change that to a fraction so that I can actually simplify this a little easier. Okay. So completing the square, I'm going to pull the 2/5 out from my x terms. And notice it's negative, so I'm going to change my sign here. Okay. And here again, you can check. If I divide out, I'm going to get 40 times 2 is 80, so that works. And then, so from there, I need to find the term that's going to make that a perfect trinomial. So again, I'm going to take 1/2 of this, which is 100, and I'm going to square that. Okay, so we'll get 10,000. And again, up here, because I've added 10,000 times the negative 2/5, I'm going to need to add 10,000 times 2/5. So negative 2/5. Here I'm going to go ahead and rewrite. So again, square root of the first term minus square root of the last term. And then over here, I can go ahead and simplify. I can divide out by 5, which makes it 2,000 times 2, which is 4,000. Okay. So from here, there's my R of X in its standard form. And this is going to answer my questions here. So the first was, what was the maximum revenue? Well, that's the K value, right? That's going to be the dollar amount. So max revenue is $4,000. And we want to find the number of units that makes us obtain this. So this occurs at our H value, so remember X minus H, so 100 units. Okay. And so now you can kind of go back and look and decide which way you like better for these. The completing the square, again, you might have some fractions or decimals in there you may need to work with, but you can also use the negative b over 2a. Again, both methods will work in finding the vertex, so it does not matter which one you choose. So in our next example, let's consider one where we are not given the quadratic function, but we still want to use quadratic functions to model the situation. Okay? So here's a typical one that you will see. A rancher with 750 feet of fencing wants to enclose a rectangular area and then divide it into 4 equal parts as shown. We want to find a quadratic function that models the total area of the 4 pens and then find the largest area that it can close. Okay? So in this case, since they're already giving you the picture, and even if they didn't, you still want to start it the same way. I want to start by figuring out my variable and then determine what my function is going to look like. Okay? So in this case, well, we've got kind of 2 variables. We've got our height of the pen, which I'm just going to call x, and we've got the width of the total pen, which I'm going to call y. Okay? And so if we look at the quadratic function that models the total area, well, the total area can be determined by x times y, right? So it doesn't matter if I look at the area here, 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 and here. The total area is basically going to be the sum of those. Okay? So if I'm looking at the sum of those, it's the same as if I looked at the whole thing. And so if I label my x this way and my y as the entire width, then I know my total area is just x times y. Okay? Now the problem with this, as we've seen before, is our functions are usually only having one variable. And in this case, I've got two. So I've got to somehow get this in just one variable. Okay? So here, if I look at this, I can use the fact that I know I have 750 feet of fencing. So I know I'm going to need fencing in each of these. And instead of thinking of this as y, I can think those sums that I have there, which is 5 of those x's, I can subtract from the 750, and then that piece that's left over, I'm going to divide it by 2 to get the top and the bottom. Okay? So here, I can rewrite my function. I'm going to call it a of x, so it's the area function in terms of my length x. It's going to be x times what I've determined my y is, which is 750 minus 5x over 2. Okay. Now, left like that, it doesn't much look like a quadratic function. So here, I just want to rewrite this. So I'm just going to separate this into two fractions, so 750 over 2 and 5 over 2, and then distribute that x through. So we're going to get a negative 5 halves x squared plus, and dividing out the 750, looks like 375 times an x. Okay, so there is my quadratic function. Okay, so there's the first part of that. There's my function that models that total area. Okay. Now, to determine the largest possible area, before I can do that, one of the things we have to think about is what we call our practical domain. Okay, so we know for a quadratic function the domain is all real numbers. But because I'm now looking at a modeling problem, that all real numbers doesn't quite make sense in the statement of the problem anymore. Right? For example, it doesn't make sense to have a negative length for my x. Okay? So here, one thing to notice is I want my domain to be such that x is in the interval. It has to be bigger than 0. I don't want it to equal 0, because if it equals 0, then I don't have a length. And I actually want to be able to form these pens. So it's got to be at least 0. And the biggest it can be, well, if I look at this piece in here, once x gets too big, negative 5x is going to be bigger than 750. So here, I'm just going to divide out by 5. So 750 divided by 5 gives me 150. Once it's up to 150, that becomes negative again. So that's what my x values have to be between. Okay? So now that I've got my quadratic function and I know which values I can use, I want to find the largest possible pen. But again, that just means I'm looking for the vertex. Okay? So in this case, I've got a negative a, which means my parabola is doing something like that. It's opening downward. So that max area is going to be where that vertex occurs. Okay? So to get my vertex in this one, I'm not necessarily looking for the largest, where that value occurs. So here, again, you can use either method, either completing the square or the negative b over 2a. In this case, both are going to be equally difficult or easy, however you want to think of it, because I've got large numbers and I've got fractions. So here, just use whichever one you like better. Okay? Me personally, I like my So I actually like completing the square a little better, so I'm going to use that method. I'm going to pull out my -5/2. Again, from there I'm going to take 1/2 of my middle term and square it. So it looks like 1/2 of that is going to be 75, squaring that. And again, I can't change my problem, so whatever I did in here, I need to make sure that I multiply and change the sign on the outside. So we have a -5/2 times this, so I'm going to have +5/2 times the 5625. Okay. From there, just going to clean it up. So -75 on d squared, plus over here when I go ahead and multiply out, so when I multiply that out, I can see that I'm going to get 14062.5. Doesn't come out very nicely. Put one back in there. But there is my completed the square for that quadratic. And this again gives me my solution. So I can look at this and see that when x is 75, so meaning when that height is 75, there is going to be my maximum area. So the max area for this one is 14062.5 square feet. Again, don't forget your units on these problems.